Welcome to the second lecture on reliability. So we'll start with faults due to non-determinism. So the idea is that does the CPU always produce the same output and always take the same time for doing so? Well, you would assume that the answer is yes, that the CPU is absolutely deterministic, which means that it will produce some output in 2 cycles or 3 cycles all the time. Not the case, no. There are many sources of non-determinism that basically make the CPU produce different outputs taking different amounts of time. Of course, it doesn't mean that you write a C program and all the time it will give you a different output. So once it will print, hello world, once it will print hi world and so on. That's not going to happen. But if we start looking at each and every output pin of the CPU or look at the memory state or many other factors, which are not supposed to be strictly deterministic for the outside world, you will see a variation, right? So in this case, in a program, you know that exactly this is what I want. But in a large part of the CPU, especially the internal parts, determinism is not required and it's not a part of the specifications. That is why we have some non-determinism, which is fine. That's an aspect of the design. See, even C programs may produce the same output, but they don't take the same amount of time and they don't have the same memory maps. So basically there are sources of non-determinism in the CPU where, as I said, a lot of the internal state can vary, even though things of interest like results of ALU operations and so on or program outputs will remain the same. But sometimes these subtle deviations from determinism, which are otherwise internal, sometimes they become external and they create bugs. So this is a problem, and in many a time what happens is that if we want to reproduce an erroneous state, it's very hard to reproduce because the execution is not deterministic. And then there is a problem, right? So if let's say we are running it on some sort of a test board, we will not be able to accurately diagnose the cause of the faults because we may see some problem. So let's say some memory pin should be 0, it is 1, but next time we run it, we may not see the problem. That is because of the inherent non-determinism, which makes it very hard to verify hardware, because unlike software, they may show a fair amount of difference run to run. As I said, some things remain constant, but many things keep changing. So let's look at some of the things that keep changing, because I've been deliberately vague in the previous slide, but let me now remove some of the clutter and tell you what is it that I have broadly been referring to. So we have random replacement policies in caches, right? In many caches, we say choose a line at random from a set and throw it out. Sometimes what happens is that bus arbiters and anything else which makes these choices for concurrent requests chooses one over the other, and many a time these random numbers are kind of set up at boot time, or because of variation of 1 or 2 cycles for other causes, it is possible that the replacement in caches will lead to very different cache states and very different performance values also. In processors, there are often uninitialized state elements, and they can cause a problem for determinism in the sense that if let's say we are relying on flip-flops, right, or transitions, and we see that they are initialized to some state, then maybe a certain transition will be much faster than others. Again, can cause some determinism, especially if we are interested in all the internal values of a processor, which means values of the internal flip-flops and so on, then life will become tough. Then, of course, power gating and clock gating are also inherently non-deterministic events, because depending upon the external voltage and so on, it may take different amounts of time to recover from a power or clock gated state. Or even DVFS, it may take different amounts of time to recover from it. So what could happen is that if I'm taking slightly longer to recover, I may miss other hardware interrupts, which may cause a system failure. It is possible that a hardware interrupt arrives at the time of a DVFS recovery and it is missed, and that causes some problem, right? But next time when I run it, it may happen that I recovered from DVFS much faster. My PLL was able to lock far sooner. So I don't get to see it. So in this case, because of the inherent unpredictability, I may see a problem, but when I try to reproduce it, I may not be able to see it. Of course, inductive noise and soft errors do lead to non-determinism, but they are rare. But since we have discussed them, I've just put it here. But essentially, it is uninitialized state elements, random replacement policies, and everything we did to reduce power. They introduce a fair amount of non-determinism. Similarly, DRAM, memory, buses, and I/O, well, the same thing. The DRAM refresh is fundamentally an analog operation, and it is dependent upon the DRAM traffic. You want the traffic to cease before doing a refresh and so on. So this can take variable amounts of time, along with the fact that we may have accumulated bit flips. So if you have accumulated them, we will have to then use the ECC bits to correct them. How many bit flips we have accumulated will be a non-deterministic figure, which is why ECC scrubbing will also be a non-deterministic figure. Again, when we access I/O like hard disks, they use mechanical components, will take different amounts of time. And furthermore, even when I'm transmitting data from one end of the chip to another, using any kind of internal on-chip bus technology, be it hyper transport or whatever. So what happens is that it typically uses a source synchronous bus. So a source synchronous bus, what it does is that along with the data, it transmits the clock. So the clock is used to recover the data. Here again, because physical transmission is involved, and also this first the receiver has to lock into this clock. Here a couple of cycles here and there can happen, right? Because latencies are not fixed, they are temperature dependent. So because of these little one or two cycles here and there, you cannot really debug a chip cycle by cycle, right? And then what can happen is that maybe there will be some fault which gets activated in some rare corner case. Let's say that you are expecting some operation to complete in 3 cycles, but it somehow takes 4. Then you may have a bug, a problem, but next time you may try to reproduce it, but every single time you'll get 3. You will never see a 4. So this will create the process of post-silicon verification and debugging. This makes them quite tough. And the reasons are all mentioned here. So the question is, can we have, for the purpose of debugging or even for the purpose of execution, a deterministic CPU, which means that its internal state for the same set of actions will always be the same, right? So again, as I said, let's not again confuse this with an executing program. An executing program will anyway always run correctly, but sometimes we may have problems in that also if we have not anticipated some rare sequence of hardware events where we kind of sat with the assumption that this will complete in 3 cycles, this one in 4 cycles, 2 and so on. But in a rare set of events, if this becomes 5 and then this is beyond our anticipation zone, could lead to problems and we may find it very hard to reproduce this scenario. So to ensure that these things don't happen and a strict contract, timing contract is maintained between all the chips elements within the CPU and the CPU itself, we would like some determinism, which means that if I set the internal state to a given state and then I run a program, then the final internal state should be exactly what I want it to be. So there are of course modern mechanisms where we can set the value of every single flip-flop, reset them, and then we can record a set of events with their precise timing. There are specialized motherboards to do that, and just replay the set of events for debugging. This will ensure that whatever I see on the field, I can reproduce it in the lab. I can reproduce it reasonably easily and predictably. And that case will not happen that I saw some 1 in a million case in the field, but I'm never able to see it in the lab. And that is why there is a need to have a deterministic CPU, not just for debugging but also for running, like a full deterministic CPU, such that wherever or whenever there is a problem and you feel that a bug happened because there's some mismatch in hardware or software or firmware, we can immediately reproduce that problem at the cycle level. That's not very hard. So let's say there's a sender and receiver, both have their local clocks. So the sender is sending at its local time TS. Then if we assume that the communication channel is timing wise non-deterministic, but otherwise kind of delivers what you have sent, but the timing is slightly unpredictable. Then we create a range. We say the maximum it can be delivered between in local time of the receiver TS plus theta 1 to TS plus theta 2. So what you do is you deliberately wait for the worst case time. So let's say theta 1 could be 4, theta 2 could be 5. So you assume that everything will be delayed till TS plus 5. Even if something has arrived early, you just buffer it and process it at TS plus 5, which is its worst possible time. So this will ensure that we are cutting off non-determinism. How are we doing that? Well, the way that we are doing that is, in case a message arrives early, it waits. Everything is processed at the right time, which in this case is TS plus 5, and this is done consistently across the board. So this will cut out a major source of non-determinism that basically arises because of long buses, or let's say it arises because of the bus slash NOC complex. So we have discussed a little bit about determinism and non-determinism. We didn't go very deep. But the basic idea was simple that look, hardware has to remain reliable, and for hardware to remain reliable, even at the cycle level, at the pin level, right, at the level of cycles, at the level of individual pins, at the level of state elements, we would like the same sequence of actions to give us exactly the same outcome as is the case in a program. The older design philosophy said that look, let all programs run absolutely correctly, but let the internal state slightly diverge. So the external state remains the same, but if I were to look at every memory line and so on, then I will allow some divergence. For instance, if I look at random replacement will always produce a correct output. It is not tinkering with the output at all. It is just that the state of the cache will vary from run to run, and thus debugging will be hard in case some problem is found in the CPU. So that is why the external output being correct, we would also like some degree of internal determinism to ensure that bugs can be reproduced in the lab, and a higher level of guarantee, correctness guarantee can be provided. Now let's look at design faults. A design fault is basically a bug, an error, right, that the designer made. You can argue that the previous category was similar. You can say that the previous category of non-determinism was similar, where the designer assumed that some interface between the sender and the receiver would, let's say, take 2 cycles. The entire protocol was based on that, but in, let's say, 1 in a million cases, because of some weird combination of the temperature and supply voltage, this takes 3 cycles. Then again, this may lead to an issue or may not lead to an issue. But the fact is that the designer, well, was not conservative enough. But that's of course one kind of bug. So to fix that, we made all communication interfaces deterministic. Because anyway, inside logic, non-determinism doesn't happen to that extent because it's still synchronized at clock boundaries. But communication across clock boundaries or between 2 circuits within the clock boundary can introduce non-determinism, as many authors have pointed out. But if we look at more core design faults like errors in adder multiplier logic, they can hurt us big time, and they in fact have hurt us. In 1995, Pentium had a very serious bug in its division unit. So it had to recall a lot of those chips. Intel Pentium, right, had to recall a lot of units, and in those days, money, $475 million, which would definitely be a billion plus today, it was spent in fixing it. AMD's Barcelona and Phenom processors had a bug in the TLB that caused the processor to hang. These are rare, but they exist, and when they manifest themselves, there is nothing that you can do. Essentially, the entire system is gone. It has to be rebooted. So, processor problems or processor design faults are very expensive because, unlike software, you can't issue a patch. So, that is why very serious verification is required. And many modern approaches are also taking the patch direction seriously. Where what you can do is, if let's say the implementation of some instruction is wrong, we can then replace it with a sequence of microcode which has the correct implementation. It will be much slower, but the point is that the microcode stored in firmware will at least give you a correct output. So such hardware patching is also happening. But the most important point is that we do so much of testing in hardware because we can't afford a bug. In the case of software, it's not that much because a patch can quickly be downloaded and installed. So the fault checking process here is that you try to avoid them as much as possible. So the typical design flow is that you decide a high level architecture, divide it into different smaller subunits, design each subunit, exhaustively test these designs. So for every subunit, you do a unit level test and then make a larger thing, and let's say it's a larger unit level test, subsystem level test, full test. Have huge testing verification teams. We'll discuss the difference between them shortly. But have huge teams just for ensuring the correctness. So there is a gold standard of correctness called formal verification, which is a formal approach where you basically say that one circuit, which is the one that you built, is equivalent to an ideal circuit. An ideal circuit may be an ideal adder or an ideal multiplier, right? So both of them are equivalent. An ideal circuit, of course, is hypothetical, it's mathematical, it's a mathematical object. And the circuit that you built is something that you built using a hardware language like Verilog or VHDL. You would like to prove that they are equivalent, which means that for all sequences of inputs, they provide the same outputs. If you define the internal state as a part of the output, well, then it produces the same output as well as the same internal states. But the key idea is that on one side of the equality equation, I have a I have my design. On the other, I have something which is supposed to be hypothetical but is supposed to be 100% correct. And I need to prove an equality or equivalence, which basically means that the circuit I designed is absolutely correct, right? Is absolutely as per specifications. So there are two approaches in theoretical CS: automated theorem proving and model checking. So here basically the theorem is that the circuit is equivalent to an ideal design. So we start with the basic axioms, right? So start with the basic. If there's an AND gate, we know what that stands for. So these are all basic axioms. And then I try to prove a theorem, which is that the output is correct by basically, saying that the output satisfies some mathematical properties. So in this case, in automated theorem proving, you don't prove that much that is equivalent to an ideal circuit, but you prove that is equivalent to an ideal mathematical model, right? So the mathematical model could not be like a full model, but it could have certain properties. So you could say that the output satisfies a set of properties and these set of properties are sufficient, right? So this would be a better way of putting it, that using known basic axioms, I try to prove a theorem. What is the theorem? The theorem is that the output is correct. What does that mean? What that means is the output that this circuit under test is producing, certain properties hold for the output, and these set of properties are sufficient to infer correctness. Model checking, on the other hand, which is a competing method and much faster and much more popular, essentially creates the model of a system in a formal language, and then it tries to check this model, again properties of the model, and again draw on some sort of an equivalence of whether the implemented system and the formal hypothetical model which is supposed to represent the problem at hand, are they same or not. So this diagram that I have drawn is more relevant for model checking, not for automated theorem proving, where I say that the circuit that I implemented is similar to a theoretical circuit, which means if the theoretical circuit is the adder, then I have a straight cut similarity over here. It's a very hard problem, undecidable in many cases, but the idea is that I take the circuit and I take a formalized model and then I try to prove properties on it. So this was the process of verification, where verification basically says that whatever I am producing will satisfy certain properties. The set of properties could be necessary, could be sufficient. Well, that I don't know. But as I said, the methods are automated theorem proving, which using axioms tries to create a theory that the circuit's output is correct. And in the other case, I take the circuit and I create a model for it using a dedicated model checking language like spin or something. Then I prove that uh, this model will not take me to what is called an unreachable state or something which is deliberately incorrect. It will always be similar in its operation to an ideal circuit, right? That is basically what I prove. Validation, on the other hand, is something where if the chip has been manufactured, then I'm kind of testing it for manufacturing defects. Verification is at the design time, or you know, roughly around that ballpark. When I'm designing something, whether I've designed, let's say, the schematic, that is when I rigorously verify. But validation is post manufacturing, where I see if what I have built is actually correctly built or not. So one testing method is known as burn-in testing. So there what you do is that you deliberately heat up the chip to, let's say, 200 to 50 degrees C, clearly out of its comfort zone. Then you attach probes to wafers, give it test vectors which are inputs, customized custom inputs, and see if the outputs match known correct outputs or not. Why burn in? Well, the idea of burn in is that you are kind of testing it in extreme conditions. If something has to fail, it will fail in that. If it doesn't fail, you kind of know it's reliable. The other popular method is scan chain based testing. So what you do is that you try to set the value of every single flip-flop within the chip by connecting their inputs to a serial bus. The serial bus is known as the scan chain. So what we do is we kind of shift in bits and transfer these bits to these flip-flops, which means that we can start from a known state and then go forward. But at least given the fact that we are starting from a known state, we are cutting off non-determinism. And then we run the processor with a given set of inputs for a certain number of cycles. The outputs are again sent to the scan chain and they are kind of read out, scanned out. So they are scanned out via the JTAG port. It's typically a serial port, but we kind of read out all the inputs and then we give it to a chip design tool, EDA tool, which kind of tells you that look, after k cycles, these are the values stored in all the flip-flops. Kindly check if it's correct or not. Then we have IDDQ testing, where you basically verify the current. So we don't do any activity, but we verify the current drawn by different parts of the chip. The advantage of this is that we can identify short circuits. We are schmooing, so we run the chip at many different voltage and frequency levels. So this will allow us to do number one, binning, which means that we can say that look, the chip is safe for only 2.5 gigahertz and below. So we'll kind of sell a 2.5 gigahertz chip and of course charge less than a 3 gigahertz chip. Also, we can create a custom DVFS table, which basically means that at a given voltage, what is the maximum possible safe frequency at which there are no errors. So we can create a DVFS table that can possibly look different for every single fabricated die because its physical properties are different. Then functional testing, which is similar to what I was saying, deterministic testing, which is that I have these specialized testing boards like Intel Golan, for example, which set the internals of the chip to a known state. So I kind of have the chip over here, put it in a known state, give it a set of test vectors, which could also be as large as, let's say, I try to boot an OS. And then I look at the outputs. If the outputs match, it is correct. So as I said, a bunch of things. Burn-in testing is when I take it to extreme conditions, I do a test. It's like functional testing at extreme conditions. Scan chain is basically a dedicated serial bus that is connected to most flip-flops. I can either set their value or read the value. Setting the value means setting the internal state of the chip pretty much. And reading the value would be reading the values of all the flip-flops or the full internal state. Can be used for testing. IDDQ and schmooing are electrical methods where first one is used to finding short circuits. The second one for binning, which means what is its safe frequency and its DVFS state. Let us look at some examples of faults. So we show three faults. They are of different types. So the first fault was discovered in IBM G3 processor. So all of these faults are regularly published by the processor vendor in errata documents, which are publicly available on their websites. They are targeted towards compiler writers, OS developers, such that they can avoid the conditions that lead to the fault. Sometimes firmware developers as well. So if you can see, this fault is activated when several conditions are true, like the L1 cache suffers a miss. At the same time, the processor is using the L2 cache and power management is active. So when all three conditions are turned on, some L2 lines may get corrupted. So this basically means that if power management is active, then well, one is either turn off power management, this condition will never happen, or if let's say you have some control over the hardware design, let's say in the next iteration, then either fix the problem or ensure that when the L1 cache is servicing a miss, don't access the the L2 cache. So that is a hardware level thing. The only software level fix is to turn off dynamic power management. Pentium 4, again several conditions that are true. There is a cache hit on a line in the M state, a snoop access is going on, and the bus you are trying to reinitialize. Again, if there is a firmware fix, which is that if the bus is being reinitialized and kind of freeze all accesses, that would fix the problem, because otherwise this may lead to a deadlock. So we will need to see if an OS fix or a compiler fix can fix the problem. Then there is no need for hardware respin, but if it's serious, then the processors have to be recalled. A new version of the processor without the bug has to be created, and it has to be given free of cost pretty much if it's happening within a warranty period. AMD Athlon, well, this is slightly different because these were events that are concurrently true in the same clock cycle. But this basically says within a window of 4 instructions, if you have an 2 a.m. adjust after multiply instructions, right, something bad can happen. Right, ALU can produce incorrect results, or if within a window of 7 instructions, right, we have a div followed by an adjust after multiply instruction, then also something bad can happen. But the nice thing is that in this case the compiler can help. What the compiler can do is that it can ensure that it will never generate code sequences that follow these properties. Of course, the casualty would be efficiency and speed, but again, this may be a worthwhile trade-off in this case, if let's say we don't want to go for new hardware. Types of faults, well, so we have discussed two variants actually without knowing that they were variants, but we'll again come back to this. So let me go to the next slide. So one is non-critical, which means they don't affect the correctness of the program. This would be issues in performance counters, debug registers, and so on. So if something is happening, we don't care that much. The other is critical concurrent. So critical concurrent would basically be the first group, where yes, the bug is critical, and you want several events or conditions to be true at the same time, same clock cycle, that is critical concurrent. That would be faults 1 and 2. The other is critical complex, where you have a sequential relationship that I have one AM instruction. Within four instructions, another AM instruction has to be there, right? So here there is a sequentiality. So this is critical complex. And the example would be the last fault, fault 3. So for us, critical complex bugs are difficult to detect because to detect them, you need a state machine. The non-critical ones, we don't care. So the critical concurrent ones is what a lot of people have focused on. How do you predict and detect? Well, the first thing is that you need to collect all events of interest. All events of interest are called signals. Now, how do you know what to tap? Well, you can look at historically things like L1 miss, L2 miss, all architecture specific things, right? So all of those can be tapped, and you just have to pray to God that whatever is a real condition, the signals for that are within this set. And also, let's say historically, a bunch of architecture specific, like processor specific things like a certain power mode or certain reinitialization mode, if that also has been involved, all of that could be tapped. And after tapping, we need a programmable combinational unit which can say that, look, yes, if signal 1, 3, 5, 8, and 10 are true at the same time, it could lead to a buggy situation. So pretty much that is how you would predict. But this is kind of predicated upon the fact that all of these events of interest are being collected in hardware in the first place. So if I were to classify these faults, I could have an alternative classification as well. I could have logic design faults where simply a mistake was made in the RTL code. I could have algorithmic faults where the RTL code is fine, but let's say that there is a high level deviation. For example, I am implementing a certain protocol. Let's say that, I'm rounding to infinity, but I was actually supposed to round to minus infinity. So in that case, my RTL is fine, but at the conceptual level, I made a mistake. Timing faults are very common. Timing faults basically say that, look, I thought that a given path would take 3 let's say nanoseconds, and I set my clock cycle accordingly. But it's taking, let's say my clock cycle is set to 3.5 nanoseconds, but this path is actually taking 4 nanoseconds. Then the signal will not reach the target latch at the right time. So I'll have a timing fault. All of these faults, which are all there at the design time, are congenital faults at birth time. So you can live with them if you wish, but then of course you'll have a buggy processor. Whether you need to live with them depends on the fact that whether you could do something to kind of circumvent it. In a lot of cases, what happens is that you can have some OS or compiler fix like turning off DVFS, for instance, if that helps. In many modern research prototypes, a lot of signals are tapped, as I just mentioned, and you have dedicated what is called DFD hardware, designed for debug hardware, that looks at these signals, computes functions on them, looks at potential buggy situations, and then either informs the user or tries to put the processor in a different mode such that these signals, at least one of them, is not triggered anymore. So some, improvisation at that point is needed to ensure that we don't actually enter an erroneous situation. So let's now look at the workarounds. So as we have been arguing, we will have to turn off some feature, right? So this part is important, that some feature has to be kind of turned off, or somehow the system has to be impaired to ensure that at least one of the conditions for the bug stops holding. That's a very important factor. Without that, it'll be hard to kind of avoid those conditions, right? So somewhere some compromise is needed. So if certain instruction combinations are the issue, as we just saw, then compiler level solutions will help. If, let's say, prefetching or DVFS is the issue, BIOS level solutions will help. So for example, stop DVFS, disable it entirely. Then we have discussed this approach based on tapping signals, where you look at all kinds of architectural events. things like DVFS, prefetching, misses, all the modes, right? Things which are kind of processor model independent and specific uh, configuration settings in the processor model which are important. So that would kind of be a conservative guess of all the signals. I would say signal is something like some event, some either some event or some setting, right? So for example, an example would be an L1 miss is being serviced, an L2 miss is being serviced, a branch miss prediction is being serviced, or we get some special instruction or a context switch or DVFX is going on, something like that, right? So then what we do is that whenever we find a bug, and a bug can be detected much later after a processor is released, we can pre-characterize these bugs in terms of these signals. So in terms of these signals, we can say that a certain combination leads to a bug, or let's say may lead to a bug, but we are sure that the bug will not happen if this combination doesn't hold. So this means that whenever a certain combinational condition is true, we can have some sort of programmable hardware. So this hardware basically means programmable hardware, and look at the impending error and take some remedial action. In the sense, if we see that something wrong is going to happen, maybe we can trigger a pipeline flush, or basically roll back to a checkpoint if a checkpoint exists, or turn off one of these things like DVFS or prefetching or something. Then we can have design for debug hardware where we create dedicated storage space known as debug buffers or trace buffers that essentially stores the values of these signals. So instead of doing an online computation on them to see if any bug condition has been triggered, what we can do is that we can analyze these trace buffers and find all the conditions associated with the bug, right? So what we can do is that if, let's say, a certain bug is happening in the field, we can then maybe send the contents of these debug buffers or trace buffers to the vendor back. It could do a fair amount of data mining and then find out the combination that essentially leads to the bug. So if this is the combination, after a thorough analysis, it can say that, look, this combination has led to this bug, right? And then what we can further do is that all the information that our hardware is collecting, again, is the signal thing. So the only difference between, let's say, this part and this part is that here we collect signals and then we compute functions on these signals. And if a function is kind of true, it will basically say that a bug may happen, might happen. So in this case, the debug hardware will collect data, and in the second case, that is, which is this case, and then we can analyze the data to find out how exactly did a bug happen. So this is kind of a pre-stage to that. So this can feed information to this. Along with that, there is a lot of work to compress these signal information that debug hardware is capturing. So we can take a single trace and kind of compress it. That would be spatial. Or we can take a set of traces for different, let's say, cores or something, and find out redundancy across time. So temporal redundancy, which basically means that if, let's say, for DBFS, for all of them is set in a column, then the entire column need not be stored. We can just store one for the entire column. So regardless of however we do it, we can do this row wise, where a row would be the signals for, let's say, one core. Or we could do it column wise, which would be the same signal across cores. Let's say L1 miss across cores, or L2 miss across cores. So it doesn't matter. In any case, we want to create a matrix where basically the rows are all the functional units, or let's say you can call it functional units or cores or whatever can generate a signal. And the columns are the signals. So it is possible that different functional units may generate the same signal. Like, as I said, prefetching or an MSHR access or an L2 miss, something like that. So we can compress data both row wise as well as column wise, Hence, they are given different names. But what is the advantage of doing all of this? Well, compression means that for the same space, we can store more. If for the same space we can store more data, we can potentially analyze more, come up with more of these bug conditions, and then use other hardware that can either avoid these conditions at runtime or at least convey this to the developers such that in the next generation of the chip they are aware that which conditions lead to a problematic situation, and then they can use it to further debug and rectify the issue. So this is the broad idea of trying to fix RTL level faults. So regardless of whatever they are, logic, algorithmic or timing, with a more solid and thorough verification as well as post-silicon validation for test chips, right? So verification is primarily pre-silicon, which happens on the design or aspects of the design. Validation, as I said, is primarily a post-silicon activity. So regardless of that, if both of these are done seriously, we should be able to avoid them. But as I said, no exercise is ever perfect. So regardless of how serious is the effort, so typically 50 to 100 bugs still slip into production level silicon. What I mean by production level silicon is basically the chip that is released to the market. So all of this is, dutifully and very meticulously documented in the errata documents. Some bugs are serious, but perhaps not that serious to recall the processor. But bugs still happen, and a lot of BIOS and I would say firmware, where a large part of the firmware is within the BIOS, and OS developers plus compiler developers actually read these errata documents and try to generate code to avoid these bugs. So this does happen. Workarounds do happen. Of course, as programmers, we don't get to see it. But a lot of people who build these motherboards and work with system software at all levels, including the OS, they are well aware that such issues are happening, and then they essentially take steps to implement these workarounds as discussed. So now that we have discussed bugs, we are ready to move to the next stage, which is discuss issues related to essentially natural variation in the fabrication process and hard errors and aging. So this I would prefer to do in the third lecture and stop this lecture right here, because we have discussed things which are of a fairly homogeneous nature, and the third lecture will be quite homogeneous for variation and aging. So we stop here and we will meet you in the third lecture where we will discuss points 5 and 6.